Welcome. In this video I'll introduce free boundary Grad-Strofanov solvers. So these are a variation on the fixed boundary I showed previously and introduce some additional complexities that we'll try and explain. So I'll introduce Green's functions, which are used for calculating boundary conditions and for modeling the coils of the plasma. Some faster ways of solving the boundary conditions, so von Herkenau's method, and the feedback control system that you need if you're solving a free boundary problem. Because in these cases the plasma shape isn't fixed by a boundary, and instead the plasma can move around, and so we need a way of controlling where the plasma moves to and what shape it has. So start by introducing the problem we're trying to solve. So we have a domain where we have R and Z, so this is major radius and height. And we have a plasma in the middle, and we have a set of coils outside. So we might have so coil up here, coil down here. And so, for example, with an X point, this X structure is produced by a coil underneath and the current in the plasma. And so if they have current in the same direction, you produce a figure of 8 kind of magnetic field, so this will continue around like this. And then in the machine we'll have diverter plates which will interrupt this, so have a magnetic field going around like this. And then here we have magnetic field going around in the same direction. Okay, so you have coils top and bottom for things like X points, and we have coils on the outside. And remember, these are needed also for shape control and for producing a vertical magnetic field. So all these coils are involved in making a vertical magnetic field to control the radial position of the plasma, and radial magnetic field for controlling the radial magnetic field for controlling the vertical position, and vertical magnetic field for controlling the radial position of the plasma. So in many cases, we don't necessarily know what the coil currents are. So all these currents. So in the inverse problem, where you have an experiment and you find the plasma solution, in that case, of course, you know what the coils are. When designing an experiment or designing a machine, we don't know what the coil currents should be, and so we specify where the coils are, and then we use constraints on the plasma shape to set the coil currents. And so there's a control system which, given, say we specify we want an X point at this location, it'll find the minimum coil currents needed to produce the shape that we want. And so that's an important part of the control system. Just like in a real experiment, the plasma can also become vertically unstable. So if your equilibrium is not up-down symmetric, you can end up with the whole plasma shifting gradually downwards and then hitting the edge of the box, just like it does in an experiment. And so this kind of vertical feedback control is also needed. So we're trying to find the poloidal magnetic field. This psi, these are contours of constant psi. So poloidal flux. This is psi, which is some function of R and Z. And then psi is a combination of two things. It's the sum of the plasma contribution. So psi is the sum of the plasma plus the coil contribution. And it's useful to split these up into two pieces. So the plasma part is due to the Grad-Strofanov equation. So here we have a delta star psi plasma. And then here we have the minus mu naught R J phi. So it's some function of R and Z. So this is the toroidal current in the plasma. We then have the coil component. The field due to the coils is the sum over all the coils of the Green's function, which is the field due to a delta function in the current, so a perfectly localized current source, which is a function of R and Z, and it depends on a parameter which is the location of the coils, so R coil and Z coil. And this is times the current in the coil. And here the Green's function is really useful. It essentially you calculate it by putting a delta function into this current. So each coil you model as a current density. So J to the coil is basically the current in the coil times a delta function in both R and in Z. So Z minus Z coil. So it's a localized current at a single point, R coil and Z coil. And then if you put this into the Grashofanov equation, you can solve it analytically, and you find that you have a solution. So there's an expression with the R and R coil. It depends on this parameter K. So little k here is this ratio here of R coil over R plus R coil, Z minus Z coil, and these here are elliptic integrals. So of the first and second kind. So this is the first kind and this is the second kind. So these can be looked up in tables or libraries, for example. And this gives a way of calculating analytically to high accuracy the field due to a coil. And in the RZ plane, it looks a little bit like this. So current here at this point, so I coil, and then close to the coil it'll look essentially like a circle. And as you go further out, it'll start to get distorted, and it'll get distorted so that it essentially twists like this. It should be up-down symmetric, of course, but apologies for that. But it gets distorted so that you can see the lines spread out on the outside and squashed together on the inside. And this, of course, is that you have a higher magnetic field on the inside compared to the outside. So this provides a way of calculating the current in the coils and the magnetic field due to the coils. And by combining it with the solution to the Grashofanov equation, we can find the total magnetic field. And then by adjusting the currents in the coils, we can find the solution that we want based on the constraints. So the overall structure looks like this. So we start with either a guess for the poloidal flux or a guess for the current, so J phi. And as part of that, we're calculating or specifying the profiles P of psi and F of psi. So these are two inputs which are used to calculate the toroidal current. That toroidal current is then solved to find psi plasma, and this is the linear solver. So solving the Grashofanov equation. And then using that, we specify work out the currents in the coils. So using the psi plasma, we can calculate the total psi by combining it with the currents in the coils. And usually this involves adjusting the currents in the coils to find the constraints. So we use a set of constraints that I'll describe shortly to calculate the currents in the coils, and then the combination of the coil currents and the plasma currents gives us the total psi. So using the total psi, we then calculate essentially the shape of the plasma. So plasma shape. So for example, find the boundary. And then that allows us to then calculate the toroidal current again, and then we go around this loop. So these are the key stages. So toroidal currents, plasma psi, total psi from the coils, and then plasma shape. And you just keep going around this loop. And typically what's done is you compare the change in psi after each iteration. So at some point here we'll check the iteration, check the convergence. At some point here, so if psi is not changing, at least within some tolerance, then we're done. So just keep going around here. Each time psi changes a bit, and we just keep going until we find a solution. So now I want to go through some of the issues and the main points involved in each of these steps. So first, look at the solver. So how do you calculate the psi due to the plasma? In a fixed boundary code, this was the main algorithm, or the main part of it. But because we knew what the shape of the boundary was, we knew what size should be there, this part was relatively straightforward. In a free boundary code, this becomes more difficult. So we have some domain, so it's usually rectangular but doesn't need to be, where we have J. We know what J phi is everywhere here, and we need to somehow calculate psi plasma. And we're solving an elliptic equation, which means we need boundary conditions. So we need some kind of boundary condition on here. But because we're not fixing the shape of the plasma, we don't know what that should be. And so there are a few ways of doing this. The first way is just to use Green's functions again. So because we know what the toroidal current is here, we can use Green's functions to calculate the psi on this everywhere on this boundary, and then we can use that psi to solve the rest of it efficiently. And so effectively we're doing an integral, so we have the psi on somewhere on the boundaries, so R on the boundaries, Z on the boundary, is the integral over the whole surface. So if this whole thing is here is S, and this is B is the boundary. So we integrate over this 2D surface of the Green's function. Of course, it's the location on the boundary, and then we're integrating over R and Z. So J phi, which is some function of R and Z. And then we integrate over dr dz. So this is a 2D integral over the whole plasma for the whole 2D domain for every point on the boundary. So if each of these sides has say n grid cells, so there's like n by n, for example, then so in total we have n squared grid cells in here. So this integral involves n squared evaluations of this Green's function, and so this is for a single point. So this is like n squared for a single point on the boundary, and therefore in total you need to do a separate integral for every point on the boundary, which is like 2 times n. Well, you'd have like 4 times n for each if you include all sides. And so the total work is goes like n cubed, because it's n squared for each point, and then there are order n points around, and so you have n cubed evaluations. And so if you have a small number of grid cells, this is maybe okay, but as your grid gets larger, this very rapidly becomes too expensive, and this becomes very slow. Because the solver in here is order n or n log n, there are some quite fast solvers for doing this part. This boundary calculation can become the most expensive, or the slowest part of the calculation. And there is a quicker way, this von Hagenauer's method, and the idea is that you solve 2 equations. So you solve the Grashofanov equation twice, but this is quite an efficient. There are efficient algorithms for doing that, and so what you do is you solve it once with a 0 boundary condition. So you solve this equation del star, and then I'll call it u, and this is minus mu dot r j phi. And you solve it once with u equals 0 on the boundary. And what you can show is that this equation, or the solution to this equation, has the following property. So you can find in textbooks, for example, derivations where the surface integrals, the integral over the 2D domain Rz of the Green's function, so this was the n squared calculation, is equal to the integral over the boundary, so this is over the length dl over the boundary, of this Green's function over major radius, and then here is the gradient with respect to the normal. So this is the gradient perpendicular to the boundary. And so here, if here this is the normal direction, which is perpendicular here. And so what you do is you solve the Grashofanov equation for u. You calculate the gradient of u at the boundaries, and then you integrate along the boundary for every point on the boundary. And so this turns it from an n cubed problem into an n squared problem. So this makes the cost, it's like n squared, because you now have an integral over the boundary for each point. And this makes it comparable to the cost scaling for solving Grachovanov, and so this makes it manageable when the grid sizes become large, whereas this becomes too expensive. So that's how we do the boundaries and calculate the psi plasma. Then we need a way of setting the currents in the coils. And so part 2 is this coil. So coil currents and control. So there are several different constraints we can set. And some common ones are, for example, we set 2 locations to be equal. So I'll call this isoflux condition. So you just say that psi at R1, Z1 must be equal to psi at another location, so psi at R2, Z2. So you just want this condition, so this could be for specifying the shape of a plasma. So you might try to constrain the inner and outer edges of the plasma. Another constraint, you might want to set the X point location, and so that's, if you have an X point, you have no poloidal magnetic field at that point. So you're saying that BR at some location Rx and Rz is equal to 0, and BZ at the same location is also equal to 0. So there's no poloidal magnetic field at that point. And so the control system's job is to find the change in coils which makes these true. And in general, this is over-constrained. So you might have either more constraints than you have coils, or in some cases you can have more coils than you have constraints. That's more rare. And so typically you need some kind of regularization. You need some way of finding an optimal set of coils. And so typically you solve a least squares problem. And so we're trying to minimize the error, and the error is given by this quite large expression, so I'll just write it out here, and then we go through the terms. So the error squared. So here I've put several different constraints. So the first one, this is an isoflux constraint. So here what this is doing is saying that this is the difference in the flux between 2 points, so R1Z1 and R2Z2, produced by a change in the coil current. And then we compare that to the current difference in psi. So this is the old solution, R1Z1 minus psi R2Z2. So this is the current difference, and we say, okay, how much do we have to change the coil current by to make this difference go to 0? The second part here is, well, these 2 pairs, these are the X point constraints. And this first one here is setting the radial field BR to 0, and the second one is setting the BZ to 0. And so these Green's functions here, these are the Green's functions for the radial magnetic field and vertical magnetic field. And so I'll describe what they are very shortly. This last one here is the regularization, and so this is essentially minimizing the coil currents, or the change in the coil currents. And so we can change what this gamma is here to make the coil currents smaller or larger, but mainly this is here to try and avoid making this an or ill-constrained problem. So the Green's functions are quite simple. So this is these GRs, GBRs and GBZs. These are just the gradients of the poloidal field. So d psi by dr, for example, gives BZ. So we write down that so we have the radial field is just the gradient of the flux, and the vertical field is just the radial gradient of the flux. And so these essentially calculate the poloidal fields due to a point current source. So by minimizing this problem, which can be done using a matrix inversion, so essentially you write this as a matrix equation for delta I coil. In general, it's a non-square matrix, so you just take the transpose and multiply through by the transpose, and that gets you a square matrix to invert. And by changing this regularization, you can make it a well-posed problem. Okay, so that's two components. This tells you what the change in the currents has to be to get the x-points at a given location, or to constrain the shape of the plasma. And then to finally close the loop, we just need the third component, which is finding the edge of the plasma. So essentially we want to constrain the current to be inside the plasma edge, and then we also want to write the current profiles in terms of normalized psi. So the normalized psi, often called psi n, is just the psi which is normalized so that it's 0 at the axis, so it's psi minus psi at the axis, which is the very center of the plasma, and then that's normalized so that it's 1 at the boundary. So this is psi at the boundary minus psi on axis. And so to define psi normal, we need to find the axis and we need to find the boundary. And so that is done by analyzing the shape of psi. So you end up with a 2D map which contains something like this. So say it's an R. So we may have x points, but they may not be exactly where we specified. We may have additional x points. So typically there'll be another x point up here, for example. And what we're looking for is an O point. So we're looking for, this is the center of the plasma, this is the axis. And we're also looking for the x points. So this is an x point here. That's an x point. So the axis is sometimes called an O point, because the field lines, the poloidal flux just forms kind of rings around it, like this. Whereas here we have an x point. And so finding these are both called critical points. So at that point we have BR is equal to BZ, and both are equal to 0. And so typically you have to do a search over the mesh and find approximations where these are. And then you can use a Newton iteration to refine the estimate and find the locations of these. You then have to find the innermost one. So if you find multiple x points, the boundary of the plasma is the innermost x point here. So in this case it would be this value here. So the surface here would be, if I mark this one, so this one here would be the separatrix, which is the edge of the plasma. And so the job of this part of the code is to find the axis, the O point in the middle, and find the separatrix. And having defined that, you can then calculate the currents inside. Using the currents, you can solve for the potential, and then you can go around the loop again. So hopefully that's helped. Those are the main components. Next video, I'll show you how this is done in practice. So demonstrate a code that does this.